Between two charged particles, we can identify the forces exerted on each using Coulomb's equation. However, there's another metric we can determine called the potential energy between the two forces. This is given by the equation U equals K Q1 Q2 by R. As you can see here, it does not follow the inverse square law, but rather a more simple inverse law. Let's say these are two positive particles separated by 4 meters of charges 1 coulomb and 2 coulomb respectively. Then the potential energy is given by K, 8.988 into 10 to the 9 Newton meters square per coulomb square, times Q1, 1 coulomb, Q2, 2 coulombs, by R squared, which is just 4 meters squared. Not squared, my bad. This is potential energy, so the denominator will not be squared. It will simply be 1 coulomb times 2 coulombs divided by 4 meters. Plugging this into a calculator yields 4.494 into 10 to the 9 Newton meters, or joules. This represents the energy stored between these two particles. Now a system will always tend towards lower energy, and you can see that as these particles grow more distant, this R value will increase and the potential energy will decrease. This reflects the repulsive behavior in which the two particles are trying to get further away from each other to lower the potential energy between the two. Now, just as force had a localized metric called the electric field, potential energy has a localized metric which we represent with this V. This V is called electric potential, which can be confusing because this is electric potential energy, whereas this is electric potential. Another common name for this includes voltage, which I'm sure many people are probably familiar with. So we can re-express V equals U by Q as its definition. So, considering this 1 coulomb particle as the source, we can determine the electric potential generated by the 1 coulomb charge at a distance of 4 meters by V equals U by Q, or K Q1 Q2 by R divided by Q, and we'll say this is the other Q, Q2, equals K Q1 by R. Plugging in K as 8.988 into 10 to the 9 Newton meters square per coulomb square, Q1 as 1 coulomb, and R as 4 meters, we can obtain the voltage generated by the 1 coulomb charge at a distance of 4 meters to be equal to 2.247 into 10 to the 9 volts.